First of all, thank you very much for watching this video. My name is Chen, and today I'm going to present a joint research with my co-author Igor Park on the topic of log concave inequality. And here is what I mean by log concave inequality. Let's say that we are given a sequence A1, A2 up to AN. Let's say that these are all positive real numbers. We say that this sequence satisfies a log concave property if, for any case strictly between 1 and n, the square of the kth number is greater than the product of the neighbor k plus 1 number and k minus 1 number. For example, this sequence here is a log concave sequence because, for example, if we take the 9 square is 81. 81 is indeed greater than 1 times 36. Right? And one of the earliest reasons why people start to study log concavity is that because log concavity together with positivity, it implies unimodality. This means that this sequence will first increases up to a certain point and then decreases until it disappears. Or in the words of my grandmother, that this object is shaped like a pyramid. Okay. And the quintessential example of a log concave log concave sequence is the binomial coefficients. Here n is fixed and k ranges from 0, 1 up to n. And this sequence is log concave because, well, you can simply verify this by direct computation. You calculate this ratio, you do some calculation at the back of the envelope, and at the end, you will get that this number is equal to 1 plus 1 over k times 1 plus 1 over n minus k. Because k is between 1 and 0 and n, this number is greater than or equal to 1. And therefore, this sequence is log concave. Okay? And here's another example. Then this time it comes from a graph theory. Let G be any arbitrary graph that's given. Let AK the number of forests with exactly k edges of the given graph, where a forest is a subset of the given graph G that has no cycle. So for example, this picture here is a forest because it has no cycle. This picture here is not a forest because you have a triangle. Okay? And unlike the previous example, where it's very easy to prove that the sequence is log concave, proving the log concavity of this forest sequence turns out to be a very hard problem. It was first conjectured by Mason in 1972, which is why it's known as Mason's conjecture. And it took around 40 to 50 years before it was finally solved by Junhe in 2015 by using this very beautiful idea, which is to take tools from algebraic geometry and convert it to something that can apply to discrete mathematics, that it can apply to combinatorics. Okay? And the proof of this conjecture and also the development of this tool was cited as one of the reasons, among many reasons. It was cited by one of the reasons for the International Mathematical Union to award the Fields Medal to Junhe in 2022. Okay. Okay. So now we have seen two examples of log concave inequality. One of them is at the level of table exercise. The other one is at the level, it takes 50 years and the field medalist to finally prove the log concavity. So intuitively, it is very, very, very clear that the second inequality is much harder than the first inequality. However, let me play a devil's advocate for now. Let me just be a contrarian for like 30 seconds. Maybe the second inequality is actually also easy. It's actually also elementary. It's just that nobody has worked hard enough to prove that yet. Okay? Now, I completely disagree with my devil's advocate. However, both me and my devil's advocates, we are both researchers. So if I want to convince him that he is wrong, I should not do it by screaming at him that you are wrong. What I should do is I should give a rigorous proof. I should give a rigorous framework to explain why or how one log concave inequality can be much harder from another inequality. That is our goal for today. This is to show, differentiate two log inequality. One is harder than the other, and we will do so by using the help of tools and ideas from the complexity theory. That is our goal for today. And of course, there are many log inequalities in the world, so we can play this game with many different inequalities. But for today, because of time constraint, let me focus only on one of them, the log concave coset inequalities. Okay. And here is what I mean by a coset. A coset is simply a set X. So today our set will always be finite, together with a partial order on the elements of the concept. For example, in this picture is a 4-element coset A, B, C, D. And here an arrow from A to B means that A is less than B. For the same reasoning, B is less than D, C is less than D, and A is less than C. And here there's actually one extra relation, which is A is less than D by transitivity, but we don't draw the arrow because it is redundant. So it's implied by the other two arrows in the picture. Okay? So this is the coset. And the topic of coset that we want to study is the linear extension, which you can view it as a completion of the partial order on the coset. For example, for our 4-element coset here, there are two possible linear extensions. Either A less than B less than C less than D, or A less than C less than B less than D. Okay? And we will write Lx equal to K. This means that our element X in the coset is the k smallest element in the partial order and the total order given by the linear extension F. That will be our notation. Okay, and now log concavity appears in the following very natural manner in the coset. Fix an element X in the coset. Let nk, where k is an integer, is the number of linear extensions of the coset where X is the k smallest element. It was first conjectured by Chern, Fishburne, and Graham in 1980, and it was proved 1 year later by Stanley in 1981, which shows that this sequence n1, n2, n3 up to nn is a log wave sequence. Now, Stanley's proof is very elegant. What he did is that it's actually basically a one-page proof. And the key idea is that he applied this very classical tool, very classical result from the mixed volume theory, from the convex geometry, that is called the Alexandrov Fenchel inequality. Forgive me for my pronunciation, as I'm not of pronouncing the name. I probably mispronounce them. I hope you can forgive me for that. Okay. Now let's discuss this inequality and this mixed volume theory a little bit. And let us, for now, only focus on dimension 2, just for simplicity. And suppose that we are given any two arbitrary polygons K and L. Let us take the Minkowski sum, which is the sum of every 2 points in the first polytop and the second polytop. That will give us this new polytop over here. Now let us take the volume of this small polytop after scaling by A and B. So you take the volume of AK plus BL, where A and B are positive variables. It's well known, it can be shown that this volume actually is a polynomial, is a quadratic polynomial in A and B, and we define the mixed volume to be the coefficients of these polynomials. Okay. One intuitive way to think about these coefficients is that you can think that this is the area that this represents the area of the larger polytop after we perform a certain way of decomposition. Okay. Now, this idea can be extended to general dimension. In the general dimension, if you are given n many polytops k1, k2 up to kn in the n dimension, then again you take the Minkowski sum lambda 1 k1, lambda 2 kn up to lambda n kn. Lambda i's are now your positive variables. And it was proved by Minkowski around 120 years later, before, that this is again homogeneous polynomials with positive coefficients. And the mixed volume of these n many polytops is defined to be the coefficient of this polynomial expansion. That is how we define the mixed volume. Okay? And now, log longevity appears in mixed volume again in the following very natural way. First, you fix the other n minus 2 polytop, k1 up to kn minus 2. Fix the values and only allow the value of the first two polytops to vary. Now, if you take the mixed volume of A and B square, it was solved by Alexandrov and Fenchel in 1927 that this number is greater than the product if you take the mixed volume of A alone times the mixed volume of B alone. And somewhat surprisingly, this inequality turns out to explain a lot of log-concave inequality in mathematics. In particular, the Stanley inequality that we saw at the beginning, this is actually a special case of an Alexandrov Fenchel inequality. When you apply, when you choose the polytops to be from the special family of these nice polytops that is called the ordered polytops. And then this number V star AB, V star A, V star BB becomes the number nk plus 1, nk minus 1. Okay. In fact, by using this argument, Stanley proved a much stronger inequality. Okay. Stanley actually proved that you can include this extra assumption, which is that you fix the extra elements y1, y2, yd, and you fix their value in the linear extension to be L1, L2 up to LD. And you only allow the value of the linear extension at x to vary and based on k. Then Stanley showed by using the same argument, using the Alexandrov Fenchel inequality, that this inequality ND1, ND2 up to NDN is again a log-concave sequence. Okay. So this is a generalization of the Stanley inequality. You can think of it as like the d-dimensional version. Okay, now that we have understand Stanley's inequality, let us move on to a problem that Stanley asked in the same paper. So in the same paper, Stanley asked for the equality condition for Stanley's inequality. That he's asking for exactly when equality occurs. Now, this is actually a very natural question to ask, because usually researchers in this area, they use equality condition as a benchmark to show that we have achieved a next level of understanding of the inequality. Which is why it's a very natural question. That's why Stanley asked this question. Okay. And now, somewhat surprisingly, this turns out to be another very difficult problem. And it took 40 years before it was finally solved for the case D equal to 0 by Fenchel and Van Hendel, where they find a combinatorial condition that characterizes exactly when equality occurs in the Stanley's inequality. The condition itself is a little bit complicated. But what is important about this condition is that it is combinatorial, that it really describes the combinatorial structure of the process. And perhaps even more importantly, that this condition is efficient to check, that this condition can be checked in quadratic time. Okay? This will become very important soon. Okay. Now that we have seen that the case D equal to 0 has been solved, it's very natural to hope that if we work just a little bit harder, maybe just epsilon harder, then we can solve this question for all values of D, or maybe for a lot of many values of D. Unfortunately, that turns out to be impossible in the following sense. Now, let us consider the decision problem where the input is a coset P and also with a fixed value D and fixed value D and K as an integer. And the problem is to decide if equality has occurred in the Stanley's inequality or not. Then, in the case D equal to 1, there's indeed a combinatorial equality condition. The condition is a bit more complicated than the one we saw for the D equal to 0 in the previous slide, so let me not present them. But what is important is that that condition is not only that it's combinatorial, the condition is also very easy to check. It can be checked in a polynomial time. However, when d is greater than or equal to 2, a phase transition occurs. Then the problem becomes so difficult that even if, let's say that we just fix our d equal to 0, just for that case alone, just for d equal to 0, sorry, just for d equal to 2, okay, d equal to 2, then this decision problem becomes so hard that not only that it's not in polynomial time, it's not even in NP, it's not even in co-NP, it's not even in any level of the polynomial hierarchy. Unless polynomial hierarchy collapses, and in that case, we have many more important things to worry about, right? Okay. This is our first main result. Okay. And now, recall that standing inequality, as we have seen before, is a special case of the Alexandrov Fenchel inequality. So in particular, this implies, because we already know that the standing equality condition is already not in formal hierarchy, and therefore it follows immediately that the Alexandrov Fenchel inequality, also the equality condition is not in the polynomial hierarchy. And that is our main result. That is the title of our talk, right? And by the way, here I would like to make a remark that actually last year, it has been shown by Sandel and Handel. They have managed to prove, from the geometric perspective, the geometric characterization for the Alexandrov Fenchel equality. So this problem is solved from the geometric perspective. However, from the complexity theory perspective, the geometric description that they have is very complicated to check. That checking that will take the exponential of exponential time, that this condition is completely intractable from the complexity theory point of view. In fact, it has to be, right? Because if the condition is somehow is not that complicated, that the condition is somehow in the polynomial hierarchy, then the polynomial hierarchy collapses, and then we will have more important things to worry about. There are many things that we will need to, we will need to rethink how we actually think about many of these complexity theory problems. Right? Okay, so this is our main result. But now, ladies and gentlemen, recall our original goal. Remember that at the beginning of the talk, we said that the goal for today is to give a rigorous way to differentiate simple log concave inequalities from other complex log concave inequality. In our case, is the standing inequality. Okay? And let us see how our result can achieve this. To do this, let us focus back on the standing inequality and consider the content and notice that it follows from standing inequality that this difference is a non-negative number, a non-negative integer. And therefore, we can construct a counting problem which will determine the exact value of this difference. Okay? And now it follows almost directly from our main result that this number or this counting problem is not in sharp P, where sharp P is the class of counting problem where the number can be expressed as the number of accepting path for a non-deterministic Turing machine. At first, when we found this result, at least for me, I find it extremely surprising. I find it very hard to believe. This is because there are indeed many inequalities in mathematics, many inequalities combinatorics that is not in sharp P. But they are usually not in sharp P because of more trivial reasons. For example, because the number involved are way too big, like an exponential to the power of exponential to the power of exponential. However, in our case, it's easy to show that all numbers involved in the standing inequality, all of them are in sharp P. So they are already reasonably small. But now we take a difference, we only make it smaller, so you will think that it's actually easier to compute, but somehow the small number turns out to become the more complicated one, right? So this somehow goes against our normal intuition. In fact, as far as I know, this is the first natural example, for log concave inequality in mathematics that is known, that has everything, the numbers involved in sharp P, but the difference is not in sharp P. Okay. Okay. In contrast to this, Let us compare this to the binomial inequality that we saw at the very beginning of the talk. Notice that all numbers in this inequality has an explicit formula. In particular, this number can be computed in polynomial time. In particular, this number is in Schottky. Another way to see why this number is in Schottky is that this difference has a combinatorial interpretation. That this is the number of pairs of non-fixed lattice path from 0 to 1, 0, 1, 1, 0 to k n minus k plus 1, k plus 1 n minus k. Where non-fixed lattice path means that this path can only go up or go right. And I want the path to be non-intersecting. Okay, this is a combinatorial interpretation. It's easy to check that this interpretation can be easily to convert into a statement that this problem is Schottky. And in fact, many combinatorial inequalities, many equalities with combinatorial proof, they also can be converted into a statement that the difference is in Schottky by using a similar argument. Okay. So now, in conclusion, we have seen that on one hand, the standing inequality is not in Schottky. On the other hand, we have binomial inequalities and also many other combinatorial inequalities for which the difference, because of how they are proved, because they have a many combinatorial interpretation, they are all in Schottky. This gives us a way to differentiate standing inequality from binomial inequality and many other inequalities, many other combinatorial inequalities. Just like what we promised at the original talk, right? Sorry, at the beginning of the talk. Okay. And I think that's what I want to say. Thank you very much for listening to the end, and please like and subscribe. Bye-bye.